To understand the origins of elements, we must journey back to the very beginning of our universe. The story begins with the Big Bang, approximately 13.8 billion years ago. In the first few minutes after the Big Bang, conditions were perfect for the formation of the lightest elements. Hydrogen, the simplest element with just one proton, was the first to form, making up about 75% of all matter. Helium, with two protons, soon followed, accounting for nearly 25% of matter in the early universe. As the universe cooled and the first stars formed, a new process of element creation began inside these cosmic furnaces. Through nuclear fusion, stars combine hydrogen atoms to form helium, releasing enormous energy in the process. As stars age, they can create progressively heavier elements through fusion: lithium, beryllium, carbon, oxygen, and so on. This process continues until iron is formed. Iron represents a critical threshold in element formation. Creating elements lighter than iron releases energy, while forming elements heavier than iron requires an input of energy. For elements heavier than iron, a more violent cosmic process is required. When massive stars exhaust their fuel, they explode in spectacular supernovae, reaching temperatures and pressures high enough to forge heavy elements. These cosmic explosions create elements like copper, zinc, and gallium through processes called the R process and S process. Even the heaviest natural elements like gold, mercury, lead, and uranium were forged in these stellar cataclysms. Recent discoveries show that when neutron stars collide, they also create heavy elements, particularly gold and platinum. Looking at the distribution of elements across the universe, we find a striking imbalance. Hydrogen, the original element, still dominates at 74% of all visible matter. Helium remains the second most abundant at 24%. All other elements, everything from lithium to uranium, together make up a mere 2% of the visible universe. This cosmic origin story helps us understand why some elements are common and others are rare, both in the universe and on Earth. The periodic table structure is designed to organize elements based on their properties and atomic structure. Elements are organized in horizontal rows called periods. Each period represents a new electron shell. Vertical columns are called groups. Elements in the same group share similar chemical properties because they have the same number of electrons in their outer shell. Elements in the same group have similar chemical properties because they have the same number of electrons in their outer shell. For example, both lithium and sodium have one electron in their outer shell. The periodic table is divided into 4 blocks: S, P, D, and F. These blocks correspond to which type of orbital is being filled with electrons. The shape of the periodic table directly relates to quantum mechanics. Each block corresponds to a different type of electron orbital: S, P, D, and F. These orbitals are determined by the angular momentum quantum number L. The periodic table's layout follows the Aufbau principle, which describes the order in which electrons fill orbitals. This filling order determines the table's structure and explains why it has its characteristic shape. To summarize, the periodic table's structure of rows and columns, together with its block organization, directly reflects the quantum mechanical properties of electron orbitals and their filling order. Every element in the periodic table is defined by its unique recipe of subatomic particles. Let's explore the 3 fundamental building blocks of atoms: protons, neutrons, and electrons. The most important concept to understand is that an element's identity is determined by its atomic number, which is simply the number of protons in its nucleus. Let's start with the simplest element, hydrogen. With just one proton in its nucleus, hydrogen has an atomic number of 1. If we add one more proton to the nucleus, we get helium with atomic number 2. Notice that helium also has 2 neutrons and 2 electrons. Adding yet another proton gives us lithium with atomic number 3. Lithium typically has 4 neutrons and 3 electrons. The key insight is that adding just one proton completely transforms an element's identity and properties. Let's see what happens when we add a proton to carbon, which has 6 protons. By adding just one proton, carbon transforms into nitrogen, with completely different chemical properties. While protons define the element, neutrons provide stability to the nucleus, and electrons equal the number of protons in a neutral atom. The arrangement of electrons in shells around the nucleus determines the chemical properties and behavior of the element. To summarize, the number of protons in an atom's nucleus defines what element it is. Adding or removing even a single proton transforms one element into another entirely. Periodic trends are predictable variations in element properties as we move across or down the periodic table. Let's examine how physical and chemical properties follow predictable patterns across the periodic table. Atomic radius generally decreases from left to right across a period as protons are added to the nucleus, increasing its pull on electrons. Moving down a group, atomic radius increases as electrons occupy higher energy levels farther from the nucleus. Ionization energy is the energy required to remove an electron from an atom. It increases from left to right across a period as the effective nuclear charge increases. Down a group, ionization energy decreases as valence electrons are farther from the nucleus and more shielded by inner electrons. Electronegativity is an atom's tendency to attract electrons in a chemical bond. Like ionization energy, it generally increases across a period and decreases down a group. Fluorine in the upper right is the most electronegative element, while elements on the left side of the table have lower electronegativity values. Metallic character describes how readily atoms lose electrons. It decreases from left to right across a period and increases as you move down a group. This explains why elements on the left side of the table are metals, while those on the right are nonmetals, with metalloids forming a diagonal boundary between them. Mendeleev's genius was recognizing these periodic patterns in element properties even before the discovery of electron structure. Our modern understanding confirms these patterns are a direct result of electron configuration. These trends demonstrate the elegant organization of the periodic table, where an element's position reveals much about its physical and chemical behavior. The periodic table organizes elements into families with similar chemical and physical properties. Alkali metals occupy Group 1 of the periodic table. These elements, including sodium and lithium, are highly reactive metals. Alkali metals are so reactive that they must be stored in oil to prevent them from reacting with air. They're soft enough to cut with a knife and react vigorously with water. Sodium is a key component of table salt, or sodium chloride. Lithium is widely used in batteries for phones and electric vehicles. Alkaline earth metals are found in Group 2 of the periodic table. These elements, including calcium and magnesium, are less reactive than alkali metals, but still quite reactive. Alkaline earth metals form +2 ions and have higher melting points than alkali metals. They're essential for biological systems. Calcium is crucial for bone formation and teeth. Magnesium is used in lightweight alloys, fireworks, and is essential for human health. Transition metals occupy the center of the periodic table in groups 3 through 12. These elements, including iron, copper, and gold, have diverse properties and applications. Transition metals are typically hard, dense, and have high melting points. They're excellent conductors of heat and electricity, and many of their compounds are colorful. Iron is the most widely used metal in construction and manufacturing. Gold has been prized for jewelry and decoration for thousands of years due to its beauty and resistance to tarnishing. Halogens are found in Group 17 of the periodic table. These highly reactive nonmetals include fluorine, chlorine, bromine, and iodine. Halogens exist as diatomic molecules and readily form -1 ions. They react with metals to form salts and exhibit vibrant colors in their gaseous state. Chlorine is extensively used in water treatment and in the production of PVC. Iodine is an essential nutrient for proper thyroid function and is used as a disinfectant. Noble gases, located in Group 18, are the most chemically unreactive elements on the periodic table. These elements, including helium, neon, and argon, have complete outer electron shells. Noble gases are colorless, odorless, and have very low boiling points. Their chemical inertness makes them useful for creating non-reactive environments. Neon is famous for its use in bright, colorful signs. Helium is used in balloons and as a coolant for superconducting magnets in MRI machines. The organization of elements into families is a powerful tool for predicting chemical behavior. Elements in the same family share similar properties due to their similar electron configurations. For example, all alkali metals will react vigorously with water to produce hydrogen gas. All noble gases are extremely unreactive, and all halogens readily form salts with metals. This predictive power allows scientists to understand the behavior of elements they haven't yet studied and helps in designing new materials and chemical processes. The human body is a remarkable chemical symphony, composed of elements from the periodic table. Just 6 elements constitute 99% of your body mass. Oxygen dominates at 65%, followed by carbon, hydrogen, nitrogen, calcium, and phosphorus. These elements are distributed throughout your body in different concentrations. Oxygen is abundant in your lungs and bodily fluids. Carbon forms the backbone of all organic molecules. Hydrogen is found in water and all tissues. Nitrogen is critical for proteins and DNA. Calcium gives strength to bones and teeth, while phosphorus is essential for DNA and energy metabolism. Each element performs specific biological functions essential for life. Oxygen enables cellular respiration, providing energy for all cells. Carbon forms the structural backbone of all organic molecules. Hydrogen participates in countless chemical reactions and helps maintain pH. Nitrogen is crucial for proteins and nucleic acids. Calcium strengthens bones and enables muscle contraction. Phosphorus is vital for DNA, RNA, and energy storage in ATP. Despite making up just 1% of your body mass, trace elements are absolutely essential for survival. Iron enables oxygen transport in your blood. Zinc is crucial for immune function and wound healing. Iodine is necessary for thyroid hormones. Copper aids in energy production and iron metabolism. Selenium functions as an antioxidant protecting cells. Manganese helps form connective tissue and bones. These trace elements support critical biological systems. Iron deficiency leads to anemia, as hemoglobin cannot effectively transport oxygen. Zinc is essential for DNA synthesis, immune function, and wound healing. Iodine deficiency can cause goiter and impair metabolism. Copper helps form red blood cells and supports nervous system function. Without these trace elements, vital biological processes would fail, despite their tiny quantities in the body. The human body is a remarkable testament to the importance of chemical elements. Though only a handful of elements make up most of our body mass, each plays a critical role in maintaining life. From the oxygen we breathe to the trace minerals that enable complex biological functions, we are walking collections of elements from the periodic table, organized into incredibly complex biological systems. Understanding our elemental composition helps us appreciate how we're connected to the cosmos and the rest of the natural world. Our modern technological society relies on an increasingly diverse palette of elements from across the periodic table. Silicon, element number 14, forms the foundation of modern computing. This semiconductor material is processed into the microchips that power our computers, smartphones, and countless other devices. Rare earth elements, a group of 17 elements in the periodic table, are crucial components in modern smartphones and other electronics. Elements like neodymium, europium, and dysprosium enable features such as vibrant displays, powerful speakers, and vibration motors. Lithium, element number 3, has revolutionized portable power. Its unique properties make it ideal for rechargeable batteries. When charging, lithium ions move from the cathode to the anode, storing energy that can be released later. Platinum, element number 78, plays a crucial role in reducing vehicle emissions. In catalytic converters, this precious metal acts as a catalyst, converting harmful pollutants like carbon monoxide and nitrogen oxides into less harmful substances like carbon dioxide and nitrogen. Our technological society depends on an increasingly diverse palette of elements. In 1900, only about a dozen elements were used in common technologies. Today, we utilize more than 80 elements from across the periodic table. Many elements that were once laboratory curiosities just decades ago are now critical components in everyday devices.